So definition of matter. What do you got, Ryan?
Anything that has mass and takes up space.
Yes, it has to have mass and take up space, right?
Yes.
Both of those two. Okay. Give an example of each of the following. Okay, so what do we know about a compound? Yeah, two or more.
Different elements combined.
Yep, different elements. I'm going to do some abbreviating. Diatomic. Yeah, these are all of our Brinkelhoffs, right? And so it can only be two, right? Atoms bound together in a covalent bond. All right, an element. What do you got for element? Okay, anything on the periodic table. That is fine. What else could we say?
The smallest form of matter still containing atom properties.
Okay, so smallest form, a pure substance that cannot. Yes, cannot be broken down. What's another word for cannot be broken down? Indivisible? Okay, we know that we could divide the atom, but if we divided the atom, would it still be right? Right? So that's one that we can say is indivisible, right? And a molecule, this is the one we were talking about that the definition is this. It can be a compound, so this is what we're going with, a compound or element, okay? So a compound or an element, and what do I want to say with it? Two or more atoms. Atoms doesn't come out. Atoms bound covalently. Okay, and we'll get a little bit more into what covalent means, but okay. So it can be an element or a compound. It's not just doesn't have to be all one type of something, okay? Does that make sense? Element or a compound. So when we say an element, so you could have H2, right? So for an example, you could have H2 here. You could also have H2O, right? Both of those are molecules. But a diatomic molecule is only one of your Brinkelhoffs, okay? So diatomic means just two atoms bound together. Compound, you can have C6H12O6, yeah? Element, we already said anything on your periodic table, okay? All right, let's jump to number 3. How many protons are there in krypton? Yeah, so we already said this, right? Krypton has a 36 up here, and this was 83 point what? You all remember 83.798? Okay, it has to be, yeah. Yes, she said what's up. Okay, atomic mass, number 4. What is the atomic mass of C5H11OH? So we would say that carbon has a mass of 0.11. How many do we have? 5. Plus my hydrogen, which has a mass of 0.08. And how many of those do we have? 11. Plus oxygen, which is 15.999. Plus one more hydrogen, which is 1.008. Now, could you have totaled all this together and said you had 5 carbons, 12 hydrogens, and 1 oxygen? Yeah, and you could have done it that way as well, okay? So what did you guys get for an answer here?
88.5.
I can't even write it there. 88.5, that's it? 1.5? Okay. And in this case, sig figs are not a big issue, but you need to know this is grams per mole because we are talking about the atomic mass. The average atomic mass. Good? All right. Well, if it says atomic mass, maybe we should go with AIM, but we're using molar mass. So no, we're just going to go with grams per moles. Let's not even pretend I was talking about that.
All right.
Moving on.
I agree.
Thanks. I appreciate your support. All All right, is that 5? Did we do 5 the other day? I moved it to 6. We haven't done any of these? Oh my goodness. I've neglected you. A sample of an element is brought near a balloon that has been rubbed on your hair. You guys have all done this, yes?
Yes.
Okay. So what happened is the electrons were transferred from your hair to the balloon. Okay? So your substance. So let's just talk about this, right? So I got my balloon. There's my balloon. All right. So what is the charge on my balloon?
It's gonna be neutral.
No. Look. What does it say? I transferred electrons to the balloon. So my balloon is negative, yes?
Yeah.
Okay. So then I took some substance and I put it up to the balloon, right? And it did what?
And it was attracted.
It's attracted. So what do you want to tell me it is?
The substance is positive.
Okay, you want to say it's positive, right? What'd you find out in your lab?
Well, it could be just temporarily polarized.
Great word. So she said it could be polarized, which means could this have been neutral
Yes.
with no charge?
Yes.
Yes. So if it was neutral, it would still be attracted to the balloon, right? Because it's momentarily polarized. How can we prove that?
Ground the object and see if it's attracted to anything negatively charged.
Okay, so you said if we want to prove that it's positive, then if I put something up here that was negative and they attracted, so they went together, you would say that what? This guy was... Could you say it was neutral? So maybe if we put something that was... What if we... Yes.
No, I said if we grounded it, though.
Okay. Yeah, if we grounded it, that would work too. Yeah. What if we put something that was positive up here? What should we see? Yeah, we should see that these two would go away from each other, right? But if this substance, let me circle it here. This guy right here, if it was neutral, what would we see?
It would still attract.
It would still be attracted. So that would be, so if it repelled, we knew that it was positive, but if attracted, it had to have been neutral because it would attract to either way. Okay. Number 6, what should we do?
You just do what we started doing on the old.
SR. And then the 187.
So you want me to do 4.35 grams SR? What's on the bottom?
And then 87.62 SR.
2.2?
No, just 1, 2.
1.2? Oh yeah, it doesn't have it. Okay. And this would be 1 mole of SR. And is that it?
No.
Yep. So you get 0.0496?
Yes.
Yeah.
And my units would be? No, moles. Moles of SR, because the problem asks you for moles, and look what happens. Grams and grams cancel out. So that the only units that I am left with are moles. Yeah. This is how I used to work every dimensional analysis problem when I was in school. I'd cross out everything and I would box my final answer, so I never got it wrong. I know that's just too much work, right? How many sig figs?
Shouldn't you have 3?
3. This has 3. Remember the first 2.
That's not important.
Right. So this has 3 sig figs, so that is correct there, 3 sig figs. And the question was, how did we get this number here? That is your molar mass, and that comes from the periodic table. Good? Okay. All right. Moving on. All right. Next problem. What'd you guys do here? 3.23 times 10 to the 23rd atoms of what? Strontium. So I need to do what? What goes on bottom? Because remember, we're trying to get to what? We're trying to get to moles. Okay, so we're going with Avogadro's number, which is 6.022 times 10 to the 23, and these are atoms, yeah? And we have 1 mole on top. How does this go into your calculator?
In parentheses.
All right, parentheses.
And XP, but, or now XP, but
Okay, so 3.23 EXP 23 divided by 6.022 EXP 23. What do you guys get? Ah, wrong problem. 0.536? Sorry, y'all. This thing has got a delay and I can't see what I'm writing. 0.536? Yeah. Units.
That's all.
Psst. Okay. Questions here? These twos are ugly. All right, number 8. Number 8 is going to be a little bit challenging. It is not fur.
What? Boots? What's the first?
No, we are not singing that song. Shut it down. Shut it down. Shut it down. There's no Flow Rider in here, okay? Shut it down. All right. It is fee. F-E. F-E. Are you guys ready for the joke? You want the joke? You ready for the joke? I think I gave this to you guys, but here we go. What do you call iron blowing in the wind? Iron blowing in the wind.
That's good. That was good. Iron Man. Iron Man. Iron Man. Because Iron Man is flying.
You made it sound.
That was good. That was
It's made out of titanium alloy.
Then why is it called
Gold titanium alloy. Because that's what they call iron.
They should call them gold titanium.
All right, so we got 167.5 grams of iron. Okay, so the question is asking us. So the question is asking us that we want to figure out what, how many electrons are freed, right? So here's the deal: if I have 1 mole of iron, that's going to give up 3 moles of electrons. Okay, so that's what this equation here is telling me. And this is okay because the law of conservation of mass says that if this is a +3 charge, which you can see there, right? And I got 3 negatives here, then that totals what? 0, which is the same as the iron that we started with, okay? But we'll get into electrochemistry a little bit later. So we have 167.5 grams of iron. So the first thing I need to do is I got to get to moles. So I know that moles is going to go on top, so it's 1 mole of Fe. And I need grams on bottom so they cancel out. So how many grams, what's the mass of iron?
55.8.
Bless you.
0.845
Yeah, 845.
grams of Fe. Ugh, this delay is killing.
Would the answer be free? When you said the joke earlier? Because it's like,
No,
It's
free.
for free.
Did you not get this?
that's funny. I get it.
Grams, go here. All right, and so I know that for every 1 mole of Fe, I get 3 moles of electrons. Okay?
How do you know that?
This equation right here tells me that.
What about it? Is it like the three? Like I just, like what are you? I see what you see in the threes, but I didn't answer.
Y'all have calculators. Put the number in. Let's go.
I got it.
8 point. Come on. How many sig figs can I have? Look, I got how many in the start? I only have 4. So 8 point what?
8.999. 9. Oh, 8.
Okay. Is there a times 10?
No.
Yeah, that's it. Yes? Okay, moles of E. I'm sorry. Crazy today. Okay. Moving on.
Harvard says how many electrons are on
Mr. White.
8.99, so about 9.
Oh, that's okay. So the answer would be 9.
No, it would be 8.99 mole. The whatever it was, moles is fine because we're not talking about individual electrons. We're talking about moles. All right, so in section 3, and I'm going to warn you for your test. If you do not read the sections, stuff like this, if you do not read it, you will not be able to answer the questions that are below it. I say that. There are some of them that you will be able to answer, but there'll be ones that are tough, and you'll be like, I have no idea where this information is. Just look above. Okay? That information is up there. All right. A student completes an investigation in which they mix solution 10 milliliters of a 2.0 molar silver nitrate with 10 milliliters of a 1.5 molar lead iodide to produce solid and liquid products in a beaker. So what's happening?
Mixing a solution to create liquids and solids.
Yeah, you mix two things and you're going to get a solid, okay? And so basically you're going to see a color change in your reaction. The total mass of the reactants was measured to be 105 grams, while the total mass of the products was 106.1. The student repeated the reaction and found that the total mass of the reactants to be 103.2 grams and the products to be 102.3. Clearly, the student is not very good.
Just roasted.
Yeah? How many significant figures are there in 103.20? Yes, there are 5 sig figs. Remember, sandwich zeros count. Zeros behind decimals count if there is a number in front. Yeah? It's a 1 through 9. List of possible macroscopic. Macroscopic meaning what? Something you can see with your eyes, yes? And a possible microscopic observation, assuming a reaction does occur. What would be a macroscopic observation that you might see? Yeah, so we might see a color change here. We see a solid produced, right? So that would be one. Anything else? What about microscopic? Is there any microscopic change that might occur?
Bacteria could die.
No bacteria.
But you don't know. There could be like bacteria in the bottom. And they just look at the
They could bond. Like the two different compounds could bond.
I think she's something about this bacteria.
When I see a color change, we see a solid. Yeah, microscopic, you would see that there would be a change. The microscopic would give you a change in the arrangement of the atoms. Mm-hmm. Yep. All right, so the big thing you need to make sure you understand is macroscopic you can see, microscopic you cannot. What is the best explanation for the difference in change in mass?
He's bad at measuring things.
Well, in the first trial, we had a difference of what? We had a mass, so we had 105, right?
It was like
0.0, and it went to 106 what? 0.1. So how could we possibly... Alex, shutty-uppy.
First thing I said all class.
Do you need one of those bars today? Mm-hmm. Or how about some shut-it stew?
What's a bar?
Shutty-uppy bar.
Oh, right.
Yeah.
Do they have peanuts in it?
Keep the peanuts out. Okay. So how could it be more? We talked about this, right? How could you have more mass? Didn't mass things properly, right? What if you had a wet beaker initially? Something along these lines, right? And then in the second experiment, what did we see?
it goes from
Yeah, so what was the mass before? We started with
103.20.
103.20 and went to what?
102.3.
How could you lose it?
Gas.
Built some.
Gas, you could spill some, you could have some residual stuff left in the beaker that didn't pour out, right? Okay, so we kind of have talked about those as we went. Write an equation in such a way that it represents the law of conservation of mass. So in this case, if we were writing this type of equation, what could we do? Like the ones I have written down there for 11. Well, let's just go ahead up and look at the problem. Let's just go up here and look at this. So Where'd it go? I missed it. All right, so what would you do? You would take what? You would take AgNO3 and what? Plus PbI2. Yeah? Okay.
God bless you.
Now, what has to be on the other side? Okay, so here's a little bit of preview of what we're going to do. Let's kind of follow this FOIL method, and I'm going to put AgI, and I'm going to put plus PbNO3, 2. Now, what would I need to do with this problem? You got to check to see if it's balanced, right? Is this guy balanced?
Wait, where are we at?
We're on 12.
Problem number 12, I believe, yeah.
Just wrote it on 9.
I just moved it up, sorry. Number 12. We're doing number 12. All right, so what do you guys see?
Besides the parentheses.
NO3, that is NO3. Complaining about my writing. Can't catch a break, man. All right, so that is NO3. All right, so what's the problem? What's the problem with what I have written up here? How many nitrates do I have on this side? How many do I have here? Nitrate groups. 1. How many do I have over here? 2. I got 2. You can't see that maybe? Oh, my screen is awful. I have 2. So, what do I need to do? Brian, what do I need to do?
You 2 what?
If I put a 2 right here, what happens?
You can't. Oh, you have 2 AG.
So it's a 2 at the end. You can't see it very well.
Then you need to move it over to
Why
where
did you add
you
the
have
two?
2 AG and
You guys, outside the screen, you can't see. It says PB. It's a 2. That's why it's in parentheses. There's 2 on the outside. Huh? Yeah, NO3 parentheses 2 at the end. So there's 2 NO3 groups there. So then over here, if you look, how many I's do I have right there? 2. So what do I need to do? I got to put a 2 right here because how many I's do I have?
2.
Only 1. So now the equation is balance, law of conservation of mass exists now. We are A-okay.
Why is there?
Here we go, Coulomb's law. Force equals K, Q1, Q2, D squared, right? All right, so let's talk briefly. K is a what? What's K? K is the constant. Q1 and Q2 are charges. And the units on this would be coulombs, yes? And then over here we have what? Distance. And this is typically going to be in meters. Yeah. And then we know that this is our force. So that's force. And we're going to have force in newtons, right? So that means that K, our constant, would have units of what? Newtons, C squared, Coulomb squared over meter squared. Right? Good. You won't need to do a lot with units though. What happens when the charge of Q1 and Q2 change? So, if I make Q1 and Q2 bigger, right? So I'm going to erase this stuff here. What happens to my force?
It becomes stronger.
Yeah, it has to get stronger because remember, if I increase, I thought somebody was snoring. No. Sorry. Okay, so if those get bigger, you guys all know this from math class, right? If I have my numerator and I have my denominator, right? If I increase my numerator, then my force has to get bigger. True? Okay. They're doing something. All right. What happens? What happens if I make Q1 and Q2 smaller? The force will decrease, right? Okay. Everybody good there so far? Okay. So what happens if I make one bigger and one smaller?
It depends on how big you make it.
Yeah, it's gonna kind of
If
depend.
it's by one, then it's not gonna be much
Yes.
difference. Like,
All right, so if we make a chart of this, right? How can we make a chart?
oh, I didn't really know how to do all of them. But for making the chart bigger, I was like, woo. Woo. Like, as the chart just got, like, increased, the force increased.
Yeah, so if I got a +1 and I got a -1, right? And then I go to it being a +2 and a -1, right? My force is, yeah, this isn't the best chart ever, but what's going to happen to my force? As I go from here to here, I would see a what?
A decrease.
Let me draw this arrow. As I go from here to here,
Because it goes from -1.
I would see an increase in my force, yes? If I went the opposite way,
A decrease.
right? So if I went this way, I would see that my force now would decrease, right? Okay. Does that make sense? Right? So changing those will have an impact, right? How what is changing the distance results in what kind of change in force?
It increases the distance, the force decreases. If you decrease the distance, the force increases.
Yeah, if I decrease, I make this smaller, then my force is going to get bigger. Okay? If I make this number, if I increase this number, right? What's going to happen to my force? Decrease, right? And this is just, all you have to understand from this is basic math, numerator, denominator, how changing one of those affects the other. Okay? Are y'all okay on that? All right. So let's do this. So if I've got, in this case, I want you guys to give me some numbers.
2, 17, 25, and 4.
Thanks. Appreciate that. I'm going to go back to my chart. All right. So I got Q1, I got Q2, and let's say that I've got,
17,
this is a 1,
24.
this is a +2. Here we've got a -2, we've got a +2, okay? And let's say for this case our distance, we're just going to say our distance, we'll go with meters, it won't really be meters, but we'll say there's 1 here and 1 meter there. Put that into your calculator and we're going to ignore K. What would happen? What would my force be? And I'm telling you just to ignore K right now because it's constant. What would we see happen to our force? What numbers do you get? So you're taking -1 times what? 2, and we're dividing that by 1. Okay? You get a number. And then your second example, you've got -2 times 2, and we're dividing that by 1. And you guys can already see what happens there. What numbers do we get there?
-2 and -4.
-2 and -4. So which one has the greater force?
-2.
Well, the greater force is the -4 in this case. Because the more you increase that charge, the greater their force is going to end up being. Okay? We don't really worry about the positive or the negative in this case. Now, let's talk about this though. What happens if my distance now, so I'm going to change my distance here. Let's go with both of these now are -2. And let's say that my distance here is a 0.3. And I drop that distance to a 0.2. What would you expect to happen?
Would the attraction get better? Or like,
Yeah, so let's go ahead and throw these in and see what happens. So go ahead and put this in your calculator. Don't forget you have to do what to your 0.3? You got to square that number. And what do you have to do to your 0.2? You also have to square that, right? All right, so what do you guys see? What's your force there? I'm just showing you. We talked through it, and I'm going to show you a little bit with numbers so that it kind of makes sense to you what's happening. Yeah? You're not going to necessarily have to calculate for your test. What do you get? Number-wise.
For the 0.3, you get negative 44.
Negative 44. And what about the 0.2?
Oh,
Uh-huh. Negative 100. Okay, so you can definitely see that as we decrease that distance, what happens to our force?
It gets stronger.
It gets stronger. So think about it in terms of this, right? If I've got two things that are attracted to each other, and I have them one out here and one out here, how great is that force of attraction? In comparison to if I take another one, and now let's say I move this one right here. What happens to our force of attraction when I move that closer? It's going to get stronger. So doesn't it make sense that if you decrease that distance, what happens? It's got to get stronger. Yeah? Okay. Hold on. Let's go. Let's go. Let's roll. Here we go. A student mixes 12.5 grams of a solid precipitate with 220 grams of a solution. 3.10 grams of gas escapes. What is the final mass of the solution? So, what's the first thing we need to do? All right, so we got 12.5 plus 220, right? And that equals what?
It's pretty tough to add that up.
I get what?
It's 232.5.
Good. Grams, yes? All right. And then what does it say? It says that. So these are my reactants, yes? Okay, so these are my reactants. Now, I have to subtract out the 310 grams of gas, right? So I keep saying 310. 3.10 grams of gas are escaping. What's the final mass of the solution? So what do we get? 229.4 grams. Now, here's the key to this problem. What are we really testing you on? Sig figs. So we're asking what happens in the lab and how does that relate to sig figs. So in this case, remember, here we go. We did what? We added, right? We got this number here, and then if we look at all of our stuff, we look at everything we start with, how many sig figs can we have?
3.
We're adding, so we have to look at what? Decimal places. So my answer has to be 229. Okay, I'll get it. Has to be 229 grams, yes? All right. Because we can only have how many decimal places?
3.
It has to be the ones place, right? Has to be the ones place. Yeah. All right. Here we go. Last one. Yeah? Is it the last one? Oh, 17's a monster.
It's not that hard.
No, actually 17's not bad.
It's really simple because we just do it. It's just like the warm within the mass.
Yeah, so here we go. We've got what? We've got 120,000 grams, yes? We need to convert that to kilograms, right? Okay, because it needs to be in kilograms. So to go to kilograms, I need to what?